Okay, now we're dealing with section 3 of chapter 1 in Chemistry, Matter, and Change, our Glencoe textbook. I am Mr. Smith. This is the Academy for Allied Health. We have first looked at a story of two substances, and then section 2 took a look at chemistry and matter, both of which to introduce substances, terms, and see how chemistry can get utilized in the world. We're now going to go and take a look at scientific methods, and following this, we'll deal with scientific research, but this section is going to be strictly scientific methods. This probably is the most important section that we're going to take a look at. We want to identify the common steps of scientific methods. We're going to compare and contrast types of data. We're going to identify variables. And we're going to describe the difference between theory and a scientific law. Now, it's very important that we cover this area and we look at it, and any questions that you have, feel free to email, talk about in class, because I want us to use this as our foundation. This is how we're going to look at everything that we do and cover in concepts and in all the subjects that we're going to have coming up. A piece of review vocabulary: a systematic approach is considered an organized method of solving a problem. This should be something we already know. What we're going to learn in our vocabulary is quite a lot now in this section. The scientific method, qualitative and quantitative data, the hypothesis and what the hypothesis means, experiment, an independent and dependent variable, a control, conclusion, coming to a conclusion, a theory, and a scientific law. The big kicker, the thing that gets kicked around, especially here in the States, that you'll see a lot, is the use of this word theory. Be careful. We are not utilizing theory as in I've just got a thought or I'm trying to brainstorm. These theories get developed in science based upon experiments that have been conducted. We're not just brainstorming. We're not flying by the seat of our pants. We've grounded our theory in a lot of experiments that have revealed X. Every time we do the experiment, X occurs. So the theory is based on that. We'll get into that as we move on. That's got to be your thought process. If you're going to state something in class, if you're going to state something as fact in class, you best have some form of reference or some experiment that you've conducted where you can point to results and say, this is why this is so. That's what theory talks about. And that's what you need to learn and how you need to act as you present and state things in class, outside of class, as a person. You want to use this scientific method. We do this systematically. Okay, we're going to have a systematic approach. We're going to be studying scientific concepts. Now, they have tried to and continue to try to use the scientific method in the humanities and in things that are sociological. Well, you've got a problem with that. Mostly in the fact that when you're dealing with sociology, when you're dealing with human issues, when you're dealing with feeling, people will react differently, and no one reacts in a uniform fashion. So the scientific method, while it's very valid for a lot of the things that we see going on, it does not really it's not really useful in the area of emotion. So it often looks very emotionless, and it actually tries to be very objective. That's actually a good thing. It doesn't want to include bias. It doesn't want to include just one point of view. That is, again, an important thing that you need to look at as we move forward in this science. This science is not designed to try to destroy how you feel about things, but it's designed to put out what is really occurring in an objective, systematic way. So whether it's chemistry, whether it's physics, whether it was biology, all of those sciences utilize a systematic approach. It is also considered an organized process used by scientists to do research, provides methods for scientists to verify the work of others. You'll learn with scientific method, when we talk about theory, we talk about scientific law, that's based on things that we call peer-reviewed. Peer review merely means that, hey, what you've done in the lab, let's say the lab report that you've written on an experiment, the reason that you write that lab report and the reason you write about your experiment is because you want your peers, you want others to review what you've done and be able to come to the same result, so that hopefully they will come to the same conclusion as you do. That's what verification is all about. That's what peer review is all about. And that's what we definitely want to push in the area of science. So this is a model, which we've talked about before. Here's a model for how the scientific method pans out. We start with, of course, observation. We all know observations, right? We've all talked about observations before. You had them with Dr. Frank. Now we're getting them here. Observation is based on a few things, though. It's not just what you see, which is the quantitative data, or what you're measuring, which is the qualitative data. You're also gathering existing knowledge, what we know about substances and things of that nature, which is why actually you're taking this course. Part of the reason to take this course is so that you can build up your existing knowledge. And that way you can move forward to find out deeper things that use this existing knowledge. Then you want to develop from the observations, we're going to develop a hypothesis. The hypothesis will be a testable statement or prediction, something that you can do and experiment on. The experiment will lead you to a conclusion. You're going to conduct the experiment and you're going to receive the results. The results are either going to say your hypothesis is valid or your hypothesis is not. The conclusion may have you revise the hypothesis, which is why that area is in a circle. Experiment, conclusion, revising the hypothesis, repeating the experiment. That's going to continue on and on and on. The idea is you want to have a conclusion that is consistent. Every time I perform experiment A, I get conclusion B. That's what you want. The more that you're able to do that, the more it allows you to then move over into the other circle, which is developing the theory. Once you've now decided to have that theory, that's based on, hey, I've done this experiment 20 times and I'm getting this result, therefore this is my theory. Based on that, other people are now going to take your data and they're going to perform the same experiment. And as you can see, they may find different areas of your theory that are true, but they may also say, hey, wait a minute, we need to revise your theory. Here's a great example of doing that in the area of the theory of evolution. In the theory of evolution, of course, originally, Dalton knew nothing about the human genome or DNA. It hadn't even been discovered or talked about yet. But he still talked about evolution. What we have seen now, because of DNA and because of the Genome Project, the Human Genome Project, we're not only able to verify even more what Darwin originally wrote about his theory of evolution, but we can see on the DNA level how DNA changes from animal to animal and species to species, wherein at this point when we say we're descended from ape, well, where's our proof? Hey, look at our DNA and genome. They are 95% similar. And that revises Darwin's theory. Why? Because Darwin didn't know about that. He said, hey, we descend from ape, but yes, how did he know? He did that based upon actually his macroscopic observations. Now that we have DNA, we can prove that there's a relationship because there's DNA in the ape and there's DNA to ours. And when you look at the genome of both, what do you know? They actually correspond super close to each other. Okay, that is what a theory is in science. That's how a theory becomes established. A scientific law, your book always talks about it being a summary of accepted facts of nature. I think about a scientific law in terms of the how. It's not the why. The theory talks about the why, and it uses the evidence of why we're descended from ape. Okay, how do we know that that's true? Because we can now look at DNA and show 95% certainty. I think of a scientific law from the standpoint of a scientific law. I can generate a mathematical equation. The most common, of course, for example, being E equals mc squared. Now, that's part of Einstein's theory of relativity. And it took a long time for Einstein's theory and his equation to become firm. But it was that equation that worked out. Another good example of a scientific law, we'll take a look in the laws of physics, the second law of Newton. It's a mathematical statement. Force is equal to mass times its acceleration. Usually it's acceleration due to gravity, but it's simply written F for force equals m mass times a acceleration. That's a scientific law. We know that it exists, and all of us actually abide by that law. We'll talk about that, of course, when we get into physics, and that's where we actually come into the idea of weight, but that's where that is. Okay, so a hypothesis is tentative. It's a tentative explanation for what's been observed, but it's not just a guess. It's very educated. Again, we need existing knowledge, we have to look at data, and then we come up with our hypothesis to test. The experiment is very controlled. We're going to test our hypothesis, which means we've rounded out to a couple of variables. So these variables can have more than one value. What we want to do is we want the independent variable as the variable we're going to change. So I know, for example, let's say I can take two clear liquids, 10 milliliters of one, 10 milliliters of another. I put them together, and in 15 seconds, I begin to see a yellow color. What if in one of those, instead of 10 milliliters, now I change it to 20 milliliters? That's my independent variable. The independent variable is changing one of those, let's say substance B. I now change from a clear liquid, from a 10 milliliters of clear liquid to 20 milliliters. I put them together, and now my dependent variable is going to be the time change. Let's say this time the yellow color shows up in half the time, much, much faster. Okay, that's an experiment. What is my conclusion? My conclusion is, okay, that means I have more of what I started with, therefore I was able to generate whatever this yellow thing is much faster. Okay, that's my independent and dependent variable. That's my experiment. Was it successful? Yes. I need to be able to repeat it now, right? I can repeat this several times. Maybe I can change the amount in substance A and control substance B and see what that does, and then come up with values based upon and conclusions based upon what I see happen with the time. That's a systematic approach. That's the scientific method. What is my control? I have a control. That's my standard for comparison. What's my control? Well, what did I start with? I started with both of my substances in the same amount. So I had the same amount of substance, and I timed how long it took for a yellow color to appear. All right? So I have that. That's my control. I've already done that. Now I'm going to vary the amounts first of one substance and then of the other. I don't want to vary both, because if I vary both, then I don't know which one might be causing the increase, decrease of speed, or showing of this yellow substance. So I want to be careful with that. I then can make a conclusion based upon the information I get out of my experiment. So the important thing to remember is we never prove a hypothesis. We can either support it or we discard it. We then can make a model to help us, based upon the results that we've seen in our experiment, we can generate a model to help us predict what will happen or what's been going on. Okay? So, two people, Molina and Rowland, in the mid-80s, they did such a thing. They conducted some experiments, they started to receive results, and then they came to everyone and they said, hey guys, we've taken a look at this and we're now able to tell you why this sudden increase of CFCs, why it's correlated to the thinness of the ozone layer. And what they did was they created a model. Here's our model, and they laid it out just like you see here. Ultraviolet radiation attacked the CFC. Because it did that, it allowed a chlorine molecule. Ultraviolet radiation is rather strong. It's electromagnetic radiation. We use a form of it to power our televisions. It is power, it's electricity. We also use ultraviolet. It lets us get our tans. It adds color to our body. Anyway, it's strong enough that it pushes off one of these a chlorine molecule off of our CFC. What happens as a result? The result is this chlorine then combines with ozone at the ozone layer, forcing off one of the oxygens. Now you have oxygen gas, which is very, very stable, and you have this new product called hypochlorite, ClO. The hypochlorite molecule then combines with an oxygen atom floating about, and you get O2 again. And notice their model. Here's where they said, guys, we've definitely got a problem. What happens? The O2 forms, the chlorine gets free, and as you can see, it's able to go back. It doesn't disappear. It's not used up. So it goes back and can now attack another ozone molecule. This can make things very, very treacherous and dangerous with the ozone layer. And that was their model. So because of that, they were able to come up with a theory that CFCs cause this problem. They noticed there's no talk about it being a scientific law of CFC. They didn't even really talk about it as a theory, but they said, hey, this causes this. And they were able to do that by developing this model and showing these results. Other people were then able to simulate that same experiment and show that same result. So it's repeatedly supported, so they get this theory, which gives us this broad principle. And that is that, unfortunately, fluorine and chlorine, being very active atoms in the upper atmosphere, will tend to break away from carbon. That usually keeps them very stable down here on the surface of the planet. Up in the stratosphere, they actually become very unstable because there's higher ultraviolet radiation, and you'll actually have a problem with the ozone layer. The theory is only successful if they can be used to make predictions that are true. Not predictions that are possibly true or closely true, predictions that are true. We then can do a lot of different experiments and eventually get to things where we can develop a scientific law where there are no exceptions to this relationship being found. Okay, Newton's law, second law of motion, force is equal to mass times acceleration, is universal. It's not. There are no exceptions, and in fact, there are no exceptions anywhere in the universe to Newton's second law. Everything. That's actually, believe it or not, why planets are round. It's because of Newton's second law. You can ask me about that. We'll talk about that when we come in the class. All right, so that's section 3. That's the scientific method. Look at how we can lay things out and come to our conclusions. That's what we want to know, okay? So a couple of assessment questions before we wrap this. Quantitative data describes observations that are numerical. That's quantitative. It's numerical. Okay? And the scientific method, what kind of approaches are they to solving problems? They're systematic. So we want to keep those things in mind. If you've answered those correctly, then you know. All right, that ends section 3. Now we are going to move on into section 4. And of course, this is just an introduction, a broad laying down of what we want to do in the area of chemistry and how we introduce this in. All right. And that's all for now.